We previously looked at conservation of mass using the convection theorem. Now we're going to look at conservation of momentum using the same theorem, which we developed in equation 66 a couple of lectures ago. This is the derivation of the Navier-Stokes equation using the convection theorem. We're going to apply Isaac Newton's second law to a moving fluid parcel, which is a small unit volume of fluid in the old sense that moves through space and time. The momentum of the parcel at time t will be defined by capital M. So M is momentum of the fluid parcel at particular time t. It will be an integration over the fluid parcel volume V sub t dy of rho, the density at time t and position y, and the particular fluid parcel momentum, velocity at time t and position y. F vector, or F vector here, will be the force density at time t and position y. Then a particular force on a particular fluid parcel will be defined as capital F of the fluid parcel volumetric integral in space-time of the force density at time t and position y over y. So once again, capital M is momentum of the fluid parcel, and capital F vector is the force on the fluid parcel. We can then define Newton's law of mechanics as the time rate of change of the momentum is equal, of course, to the force on the fluid parcel. So this is where we're applying Newton's law. Now we take this and apply it to the convection theorem, and we can write that the integral over the fluid parcel is equal to the material derivative of the momentum per unit volume plus the momentum per unit volume times the divergence of u, which is of course the definition of the convective theorem, is equal to the right-hand side sum of forces, which will be F dy, which we move to the left-hand side here. Now using equation 71, which was the conservation of mass equation, and taking an infinitesimal volume element V naught, we can find equation 78, which is rho times the material derivative of U is equal to F, the forces. We can also expand this out through material derivative and write rho times partial U partial T plus U dot nabla U equals F, the sum of the forces. Recall that U dot nabla is nothing but the sum of UI partial I. So here is, of course, our core Navier-Stokes equations. We still need to figure out what the right-hand side is. We can evaluate everything on the left easily. We're looking for rho, and we're looking for U. We may not know those, so they're variables we're solving for, but we need to figure out what the forces are on the right-hand side to complete it. And we'll mostly consider external and internal forces. External forces might be like gravity or electromagnetic forces. Internal forces might be things like pressure or friction.